Welcome back, students. In the last lecture, we discussed mass transport and diffusion in gases. Today, we will discuss other forms of transport for gases. We will look at the transfer of energy in a process called thermal conduction and the transport of linear momentum in the property called viscosity. After this, we will have a brief discussion applying these ideas that we developed for gases to liquids to describe diffusion and viscosity in liquids, which is important for chemical reactions. The learning goals for today are going to be to describe transport of energy and momentum in the above described phenomena. And we're also going to want to understand how the kinetic theory of gases is successful in treating these and how it fails to completely describe these. And then we're going to talk about, again, applying this to liquids with the concept of Brownian motion. So we'll start off with thermal conduction. Molecules store energy in their degrees of freedom, which results in an increase in temperature. Just like for diffusion, we can model a temperature gradient in a gas. Note we're using a similar plot here. We're using a similar description using the mean free path and so on. As hot particles move from the hot side of the container to the cold side of the container, the temperature of the cold side will increase and the temperature of the hot side will decrease. This discussion will ignore other forms of energy transfer. So some of these you have probably heard about. Convection, like your convection ovens, where there is a current that directs the flow of particles as the heat flows around. We're going to ignore that. And also a radiative transfer, like black body radiation, in which particles are actually radiating energy outside of them. We're going to just deal with kinetic theory of gas descriptions here. Note that this discussion, the gradient is restricted to energy and temperature only. So if we look up here where we have our gradient, the number of particles is equal throughout the container. What's different is the temperature. So there's a hot side of the container and a cold side of the container. This means that the particle flux will be even. So the number of particles moving from the hot side to the cold side will be the same as the ones moving from the cold to the hot side, but the hot to the cold will be transferring energy across the gradient. So we're going to be looking specifically at the transport of energy and again, using thermal conduction. We describe the energy distribution in the same manner that we described the particle distribution with a Taylor series expansion. So the energy at point lambda, negative lambda, is simply equal to the energy at point 0 minus lambda times the change in energy with respect to position. Again, this dE dx here is simply the slope. So we can calculate the energy at a different point by adding the slope and multiplying by the distance we've deviated from our starting point. We can say the energy at point lambda is equal to the energy at point 0, in this case, plus lambda times the slope. So with these, we can determine the energy at 2 different points. Again, just like for diffusion, the flux and energy can be described mathematically. So in words, the flux and energy is going to be the number density of particles, how many particles are crossing the flux plane, multiplied by their velocity. So how fast are they? How likely are they to move across the flux plane? And then it's going to be determining the energy of the particles. So multiplying all these things together, the flux across the flux plane, here centered at x equals 0, is going to be the number density times the energy of the particles as a function of x. And then we're integrating over, in this case, the forward velocities. So Vx, our velocity function in the x direction, dVx. We've done this integral enough times now to know that it's 1/4 times the average velocity. So that gives us the following expression. The flux of energy is equal to 1/4 times the particle density times the energy of the particles as a function of x times the average velocity. To figure out the net flux, we have to add the flux in the left and the right directions. So our total flux is going to be equal to the flux from minus lambda to 0 minus the flux from lambda to 0. So that's going to be 1/4 times the number density times the energy at negative lambda times the average velocity, minus 1/4 times the number density times the energy at positive lambda times the average velocity. We can plug in the definition for the energy at point negative lambda and positive lambda into our equation here. And that will give us 1/4 times the number density times the average velocity. And then our energy at negative lambda is simply the energy at 0 minus lambda times the change in energy with respect to position. And then our energy at positive lambda is our energy at point 0 plus lambda times the change in energy with respect to position. Here we can see that our energies at point 0 will cancel, and what we'll be left with is negative 2 lambda times the change in energy with respect to position. So pulling out the 2, we get minus 1/2 times the average velocity times the number density times the mean free path. And then we have the change in energy with respect to position at x equals 0. To introduce temperature into this, we'll note that for monatomic gases, the energy is simply equal to 3/2 kT. So we'll substitute in 3/2 kT for the epsilon. 3/2 and k are constants. So we can pull the 3/2 out and the k, which will give us minus 3/4 now times k times the average velocity times the number density times the mean free path. And now we have our change in temperature. So we've established a temperature gradient with respect to x. In this discussion, we have assumed that we are working with a monatomic gas. This assumption here is only true for monatomic gases. For example, a diatomic gas with very little vibrational energies accessed would have an energy that's equal to 5/2 kT. So how can we properly treat these things? For a monatomic gas, the molar heat capacity was simply equal to 3/2 R. If we divide this to get it into individual molecule units, if we divide this by Avogadro's number, that turns our R into a K. So the molar heat capacity for an ideal monatomic gas divided by Avogadro's number is 3/2 K. Moving over for our diatomic gas, the same thing is true. So CVM over NA would now be 5/2 K. And so we can, instead of using this assumption of relating energy to temperature, we can actually just use the heat capacity. So we can substitute in CVM over Avogadro's number for 3/2 K. What that gets us, if we make that substitution in here, this gives us that the total flux is equal to minus 1/2 times the heat capacity over Avogadro's number times the average velocity times the number density times the mean free path times finally our temperature gradient with respect to x. We had to make the same correction we did for diffusion, where we multiply this by a factor of 2/3, and the 2/3 here counts for motion in all directions, not just linear directions. And that gives us a total flux being equal to negative 1/3 times all of our constants that I just mentioned. Now, with this, again, we have the same thing we saw for diffusion. We have a whole bunch of constants multiplied finally by some gradient in one of these macroscopic variables. So all of these constants here get pooled together in the thermal conductivity kappa. And so we can say that the total flux is simply equal to negative kappa, the thermal conductivity, times the temperature gradient with respect to x. Just like for the diffusion coefficient, our thermal conductivity depends on the kinetic theory of gases and can be used to estimate the hard sphere radii of gas particles. We can actually test this model by investigating the pressure and temperature dependence of kappa. The kinetic theory of gases predicts that parameters such as the mean free path and the number density depend on things like temperature and pressure. So how does this model predict the temperature and pressure dependence of our kappa? If we go ahead and substitute in the actual expressions for all of these terms here, we see that the average velocity is equal to the square root of 8 kT over pi times the mass. The number density is the pressure over kT, and the mean free path is kT over the pressure times 1 over sigma, the collisional cross-section, times the square root of 2. What we know is that the pressure terms in this equation are going to cancel, and we would actually predict that our kappa is independent of temperature, since it's in the numerator and the denominator. These two temperatures will also cancel, leaving a square root of temperature dependence for kappa. So how does this model do? Well, looking at the data here, we can see that the model actually is borne out to some extent in reality. So if we look at nitrogen and argon, a monatomic and diatomic gas, both gases are relatively pressure independent for a large amount of pressures. So from about 1 atmosphere to maybe about 50 atmospheres here, these gases that have a relatively pressure independent thermal conductivity. And then over a pressure of about 50 atmospheres, the thermal conductivity starts to increase. Why does the model break down at high pressures? Well, think about it. At high pressures, we're forcing these gas molecules to interact with each other. So part of our kinetic theory of gases is that the gas molecules are isolated. At very high pressures, this is not true. They start to interact with each other. That's going to bring about things like van der Waals interactions, favoring liquids and overall breaking down our hard sphere model. A similar thing is true for the temperature. So the temperature prediction here, you can see the plots are the square root of the temperature. And the plots kind of sort of match the experimental data. It's not super good, and this is for the same reason. So in our model, we've neglected molecular interactions, and that causes the data to only be so good in terms of fitting to the model. We can describe the flow of linear momentum in the same way. This may seem a bit out of left field. Why are we talking about linear momentum, and how do we transfer it? Linear momentum is simply the linear velocity, which is just the velocity, multiplied by the mass of particles. So imagine a gas flowing through a pipe. If we imagine this gas flowing through the pipe, gas in the middle of the pipe is going to move faster than gas at the edges of the pipe that have to deal with the edges of the pipe. This creates a gradient in velocity, as can be seen here. The particles in the middle are moving faster than the particles at the edge. So the particles in the middle have a higher velocity and therefore a higher linear momentum than the particles at the edge. Gas molecules will not only flow through the pipe in the forward direction, but they'll also move around in the y and z directions, creating a gradient, a motion against a gradient of linear momentum. And this process can be described using viscosity. The derivation for this equation is exactly the same as we just did for thermal conductivity and what we did last time for diffusion. So we can set up a gradient. We can talk about the momentum, the linear momentum, one mean free path away from the flux plane, and talk about particles moving. In this case, note that we're talking about particles moving in a different direction than the flow. We're talking about kind of swirling along as they flow here. And we can go through and use the same approach as before, and we end up with a very similar expression to what we saw before. And that is the total flux is equal to a whole bunch of constants, so negative 1/3 times the average velocity times the number density times the mean free path times the mass of the particles, and then times a change in velocity in the x direction with respect to z in this case, because we don't have an x direction, we have a different dimension here. And we'll pool all of these constants together under the symbol eta, which is the viscosity. So the viscosity is talking about how particles resist moving amongst themselves. And this eta here is the symbol for viscosity. For units, we often use 1 poise to talk about viscosity. And 1 poise, note that poise is not an SI unit. So 1 poise is 0.1 kilograms per meter per second. So we do have to do a conversion if we ever want to convert poise into SI units by a factor of 10 there. It is common to report viscosities for gases in micropoise and liquids in centipoise to talk about kind of the magnitude of their viscosities there. Just like for thermal conductivity, viscosity of gases is expected to be independent of pressure and proportional to the square root of temperature. And you can go look up the figures in your book, and they look almost exactly the same as these figures here. The same simplifications have been made and the same errors that come about. Lastly, we will discuss diffusion and the viscosity of liquids, which is typically where we think of chemical reactions happening. Motion in solution is referred to as Brownian motion, named after Robert Brown, who first observed this type of motion by putting pollen grains in water and watching them under a microscope. This random motion is also applicable to smaller particles like molecules. Particles in solution are jostled around by collisions with other molecules. This will cause a force to be applied to these particles. And we can talk about this force because it's opposed by friction, which has to do with the viscosity of the solution. So in this, we come up with a differential equation where we talk about the mass times the acceleration is equal to the force being jostled around by motion of the particles and then being opposed by the frictional force. And so we can come up with an equation, and the person who actually came up with this equation is Einstein. And so Einstein analyzed the equation, solved it, and found that the average square of the displacement here is equal to 2 times Boltzmann's constant times the temperature times time divided by the friction. If we assume that the particles are spherical, the friction becomes 6 pi times the viscosity times the radius of the particles. And so we can plug that in there and look at this formula. We previously noted that the RMS displacement, which is the square root of the average square displacement, was the square root of 2 dt. So that means that the average square displacement is 2 dt, and therefore our diffusion coefficient is equal to this stuff in the middle here, the kt over 6 pi times eta, the viscosity, times r. And this is the Stokes-Einstein equation for diffusion. This equation is appropriate when the diffusing particle is significantly larger than liquid molecules, like pollen motion, like Brown noted, also for things like ribosomes, or ribosomes are significantly larger than water. If the molecule is approximately the same size as the solvent, a modification needs to be made to model self-diffusion, and the diffusion coefficient, essentially we swap out the 6 for a 4 to talk about self-diffusion. Unlike gases, the viscosity of liquids actually increases as temperature decreases. We were familiar with this from pumping gas in the winter, where the gas pumps much slower because it's more viscous. This is because when liquid molecules are cold, they have less energy to overcome their intermolecular interactions, making them more resistant to motion and therefore more viscous. So with that, we will be done discussing transport phenomenon. The conclusions are we have these transport properties such as matter, energy, and momentum, and we can describe the transport of these properties with diffusion, thermal conductivity, and viscosity. Lastly, we can actually make a pretty accurate model for diffusion in solution, modeling Brownian motion using the Stokes-Einstein equation. In the next few lectures, which will be the remaining lectures for the semester, we'll actually apply all these ideas you've been talking about in the last few weeks to describe chemical reactions and the kinetics of those reactions.